Thank you very much for coming. And tonight we're going to have Stephen White talking on fine-tuning and the multiverse. And so, Steve, I'd just like to hand it over to you now.
Okay, thank you, Kevin. I'm not sure if I am the inaugural. I think we had you, Ross, speaking all the way from California about a month and a half ago, didn't we?
Yeah, but with that one failed, we didn't get it recorded.
Okay. Anyway, thank you for all tuning in tonight. Sorry we won't have supper. We're having to do this remotely. As you can see from the top there, this subject is fine-tuning in the multiverse. I do have a science degree, largely in physics, so it's somewhere along the lines of what I think I can speak a little bit about anyway. Right up front, we have that probably one of the most iconic images that NASA ever took. As you can see down at the bottom there, the pale blue dot is taken from the Voyager 1 spacecraft in 1990, February 1990, looking back from beyond the orbit of Neptune. That now is the last official planet, the most furthest official planet in the solar system, because Pluto got downgraded a few years ago. But yes, there it is, the little blue dot looking back. So how significant or insignificant are we? Well, according to Richard Dawkins, anyone who has a physics degree is studying only simple things, and we do not attempt to invoke design. Back to that image, what does Stephen Hawking say about it? We're such insignificant creatures on a minor planet of a very average star in the outer suburb of one of 100 billion galaxies. So it is difficult to believe in a God who would care about us or even notice our existence. Having said that, here's another scientist, a Nobel Prize winner. Humanity appears to be part of a remarkable set of circumstances involving a special time around a special planet which orbits a special star, all within a specially constructed universe. You can see there the reference, Professor Brian Schmidt, astrophysicist and a Nobel Prize winner. And he gives the foreword to the book that I'm going to use largely in this presentation tonight. The book, Fortunate Universe, Life in a Finely Tuned Cosmos by Geraint Lewis and Luke Barnes, written in 2016. Now let's just hark. You can see the book on the lower right, A Fortunate Universe. Back when our chapter first started about 8 years ago, we did go through the book On Guard, William Lane Craig, who of course is the founder of Reasonable Faith Organisation. In chapter 5, we did look at fine-tuning. Going to that particular chapter, though, it really only quotes two of the actual physical elements or aspects of fine-tuning. One was the amount of the weak nuclear force and how accurately it was tuned. And then he talked about the entropy, that is the disorder in the universe at its beginning. He then went on mainly to philosophical things. But in the vein of so far this year, we are now going to try and focus a bit more on actual physical explanations, and that's where A Fortunate Universe comes into its own, and it actually provides graphs. I did look on a number of different sources, and it was quite interesting to note that there was no agreed number of finely tuned items, or that is aspects of the universe, and constants. So it was a bit difficult to define how I should go ahead, but once I got to A Fortunate Universe, I felt this one gave a fairly good explanation of a number of different the constants and forces, and so we're going to look at those from this particular book tonight. Even so, as I introduce you, you'll see there are some other constants and other things that are finely tuned as well, but that book, A Fortunate Universe, is the one that I'll be using as my main focus tonight. So we'll look, as the outline, we'll look at the ancient conclusions about our universe. We'll look at recent history of the fine-tuning arguments, the elements required for life, the fundamental forces, fundamental particles, quantum mechanics and Planck's constant, density of the early universe, the multiverse theory, and Richard Dawkins again. I've got to quote Richard Dawkins. He is one of our main antagonists, so it's important that we don't forget to mention him. So let's go back into ancient history. According to Plato, there are two things that lead men to believe in God: the argument for the existence of the soul and the argument from the order of the motion of the stars. Now, you could go back all the way to ancient Babylon and the Sumerian civilization, the first civilization from the Mesopotamian region, and they, in Babylon, certainly studied the stars. They recorded all sorts of aspects, and they wrote the sequence of the reappearing order of the stars. So it's something that goes right back to the ancients, and certainly by the time we get to Plato, about 400 BC, he certainly considered that was one of the arguments for someone who made things. In other words, the belief in a God who made everything in order. His successor, or one of his successors, Aristotle, certainly came to a similar conclusion. I'll just skip down here, and his title in the first uncaused cause, which is God, a living, intelligent, immaterial, eternal, and most good being, who is a source of order in the cosmos. Again, they looked up to the stars and they saw order there, and that to them was something that wasn't just an accident. It was something there that was caused by a supreme being. Of course, I could go back from a religious perspective to King David, but probably sat out there before he was a king as a shepherd, looking at the stars as he minded his sheep on the night and looked up at the night sky, and was able to write then in one of his psalms, "The heavens are telling the glory of God, the firmament proclaim his handiwork." And of course, there's another verse there. And then we go to St. Paul, who also reached the conclusion that the creation of this world, ever since the creation of this world, his, meaning God's invisible nature, namely his eternal power and deity, has been clearly perceived in the things which have been made. He doesn't refer to the stars there, but he certainly came to a similar overall conclusion. Now, let's see if that was just ancient heresy, ancient wishful thinking. Surely it was all swept away during the age of the Enlightenment. We don't believe those things anymore, surely. Well, let's have a look. 1913, chemist Lawrence Henderson wrote The Fitness of the Environment. Henderson discussed the importance of water in the environment with respect to living things, pointing out that life depends entirely on the very specific environment conditions on Earth, especially with regard to the prevalence and properties of water. I'm not going to go into too deeply here, but as he pointed out, at 1 atmosphere and at about 35 degrees centigrade, water is in its most useful and state in which it can actually go between its different phases. So our actual environment here at the surface of the Earth is just about the best place for water to be used in its different aspects and phases. Moving on a bit from 1913, 1961, physicist Professor Dick claimed that certain forces in physics, such as gravity, electromagnetism, must be perfectly fine-tuned for life to exist anywhere in the universe. Then go on to Professor Fred Hoyle, someone is often quoted, and he quoted in his book, The Intelligent Universe, the list of anthropic properties, apparent accidents of a non-biological nature without which carbon-based and hence human life could not exist is large and impressive. Indeed, it was Fred Hoyle who got his Nobel Prize for proposing how carbon was indeed generated within stars. And finally, 2001, Lord Martin Rees, past president of the Royal Society, current astronomer royal, even to this day, and an atheist, listed the fine-tuning of the universe in terms of the following 6 dimensionless physical constants. I won't go into any great detail. There's just a listing to show that even an atheist can recognise the very fine tuning of a number of the constants we have in our universe. First of all, the strength of electromagnetism to the strength of gravity. Epsilon, measure of the nuclear efficiency of fusion from hydrogen to helium. Omega, commonly known as the density parameter, is the relative importance of gravity and expansion energy in the universe. Lambda, commonly known as the cosmological constant, describes the ratio of the density of dark energy to the critical energy density of the universe. Q, the ratio of gravitational energy required to pull a large galaxy apart to the energy equivalent of its mass is around 10 to the minus 5. And finally, the number of dimensions in space-time is 3. Reese claims that life could not exist if there were 2 or 4, though he does agree that he contends down the bottom there, this does not preclude the existence of 10-dimensional strings. And we'll talk a little bit later about that concept when we get to talk about the multiverse. Right, now let's turn, we've introduced these statements by people, both in the past and in more recent times, about what they see as the means of the fine-tuning that they see in our universe. Now I want to focus particularly on life. After all, how is life able to exist on this earth? I brought up this picture of the periodic table of the elements, or the different matter that indeed then forms to provide compounds from which we know in our particular planet. Starting at the top left, we have hydrogen. And that must combine with oxygen, nitrogen, carbon, form the hydrocarbons that we know in life. We also should mention that we have phosphorus there as well. I won't include the silicon or sulfur, but certainly those top 3 are necessary to combine with hydrogen before we know about life. We have sodium, manganese, potassium, and of course calcium in our bones. We have iron that flows and gives the red colour to our blood to bring the oxygen from what we breathe into the rest of our system, into the all the different parts of our body. And then we have chlorine. Chlorine combines, of course, with sodium to make salt, which we need, bromine, and last but not least, iodine. For those that might suffer a goiter, iodine, of course, is added to salt, and it's iodine that helps our thyroid work to regulate our metabolism. So all of these atoms are necessary if life as we know it is required. So how do these atoms form? That's the big question. If we'd started off at the beginning, only hydrogen was there. So how do we get to all of these? What is the necessary conditions that we should have these? And of course, there are many others there. I might then go on to mention the things that we desire in life: copper, silver, gold, platinum, all things that we like. And of course, remembering way back into ancient history, we also had arsenic and tin, which when they added to copper produced bronze, the first of the metals, or the compound metals, the alloys, that was used in ancient civilizations. Right, well that lays down the elements that we would regard that we need for life. Now let's go back to a more microscopic stage. We're going back now to what makes up the particles, the fundamental particles. First of all, we have the quarks, and this is taken on, give reference to a slide that Kevin put up when he first presented at the beginning of this year. So we have the quarks, the up and down quarks, and the others there. We have the leptons in green, and the blue force carriers, the bosons. Just a reminder, in the beginning, radiation from the exploding singularity as it went out converted into fundamental particles, which in turn formed into protons and neutrons. This is how we're going to get what you saw on the previous slide, the elements. How do we get to those elements? Well, we needed protons and neutrons, and the basis of hydrogen and its isotopes, deuterium, which was hydrogen and 1 neutron, and tritium, hydrogen and 2 neutrons. All of those came because according to the standard model, singularity exploded first of all into radiation, which in turn turned into fundamental particles, which in turn then formed protons and neutrons. And we'll talk about these a little bit later as we get further into the discussion. Okay, having got those deuterium and tritium, how did they then combine to make the elements? We're going to start on the first stage. This represents is an image of the Hertzsprung-Russell diagram. some of you who've done physics and astronomy in the past will recognize it. We have a chart of the stars. Generally, we believe the blue ones up the top left started in were the earliest of the stars, the youngest of the stars, and gradually as they consumed hydrogen, turned into helium. During the mainstream, they gradually grew lighter before they turned into more or less the colour of our sun down here in the middle of the diagram, before gradually turning redder and redder and redder, and then in fact becoming red dwarfs. But there were outliers. We have the giants over here on the top right and the white dwarfs down below. That's the background to how the stars progressed and how, as we're about to explain, the elements that were necessary for life were formed. You'll see here the diagram over the top right here towards the bottom, we have deuterium, one of the isotopes of hydrogen, colliding with tritium to form a helium particle. And that was right happening in the blue and the white region of the stars. So that'll get you two of the elements, but we don't need helium particularly unless you want to blow up balloons. So helium is really only a stage to getting to the elements that we needed for life. As the stars used up hydrogen, as I said, they cooled and they turned yellow, then red. The core of the red giants in particular had enough gravity to start smashing the helium together. Helium, then when combined, would go to beryllium. Beryllium, when combined with smashed into another helium, would then form carbon, obviously one of the major elements that we need for life. And of course, it would also emit radiation. Indeed, in every stage of this collisions, we're actually talking nuclear fusion, then yes, there is a generation of radiation which then continues on to perform further effects of the fusion. Now, just briefly, while we're talking about things, I'll bring up the fact that on this particular chart, you'll see Betelgeuse. I'm never very good at how to pronounce that, Betelgeuse, but then also we have Rigel, one of the blue supergiants. Just to put it into perspective, this is not just a chart, it's not something that scientists look at. You can actually go out to the night sky, and if you look up at the Orion Constellation, there is Betelgeuse. See? If you see, there's the belt, Orion's belt, and if you look up in one direction perpendicular, you'll see a yellowish star, quite a bright yellowish star. That's the big red giant up there. Similarly, if you look the opposite direction, perpendicular down through the belt, you'll see actually a bright, very bright white star, and that is Rigel. So what I was explaining about in the charts on the previous slide are not just things you'll see in textbooks. You can actually go out into the night sky and see it all there. And those are representing, somewhere in the case of Betelgeuse, a red giant that was probably compressing the helium, turning it into carbon, as we saw a few slides back. Heavier elements are also formed in supernova and quasars. In other words, wherever there's massive compression, then you're going to smash the lighter elements together and produce the heavier elements that we saw in the periodic table a few slides back. Now, how does that all relate to fine-tuning? Our sun is exceptional. We are a minor planet of a very average star on the outer suburb of one of the 100 billion galaxies, according to Stephen Hawking. However, in New Scientist back in 1999, there was an article, "Our sun is exceptional." Our sun's location. It's a single star. Most stars exist in multiple star systems where planets suffer extreme temperature variations. Luke Skywalker up on Tatooine would have had some real problems on his planet because one of the stars would have produced baking heat, the other probably would have done something else. We have a single star. We know what it's about. It goes down in the evening, comes up in the morning, and we don't have to worry about other stars coming out at different suns coming out at different times. The sun's position in our spiral Milky Way galaxy is ideal. Its orbit is fairly circular. It doesn't go too near the inner galaxy where supernovae are most common. In fact, if you excuse me, I'm just going to turn off my emails. They keep flashing at me and making me get rid of them. Catch up the emails later. So yeah, the sun is orbits are fairly circular. We don't go too near the inner galaxy, where of course you've got a big black hole and lots of other stars, many of which are giant, which would certainly fry us. Its orbit's almost parallel to the galactic plane. Otherwise, we'd be crossing the plane would mean we'll be going in and out of dense star regions. We don't want that either. The sun is an ideal distance from the galactic centre, called the co-rotational radius, where a star's orbital speed matches that of the spiral arms. Otherwise, the sun would cross the arms too often and be exposed to supernova. Our sun is an exceptionally stable star. 3 astronomers studied single stars of the same size, brightness and composition of the sun. In fact, it's that reference down there again in New Scientist back about 1999. Almost all of them erupt about once a century in superflares 100 to 100 million times more powerful than the one that blacked out Quebec in March 89. Not all of you will remember this, but just a reminder, yes, back in 89, we're in the middle peak of the solar cycle, and there was a particular flare that came out, and all the power lines in Quebec ended up getting inducted by this, the particles coming in from outer space, and blew all the fuses, and Quebec was dark for quite some time until they managed to reset all the fuses. So yes, we're grateful we don't live in a star like most of the others, which put out big flares, a lot more powerful than the one we experience in our very stable star. Now I'll focus in on particularly on to a fortunate universe. Up to this point, I've been looking at general aspects, trying to lead in, and at the same time taking the aspect of our star, which I think was important to introduce, because it's not actually covered so much in the fortunate universe, but it's something that I came across. I felt that I wanted to remind you of just how stable and what a very special region of our own particular Milky Way that we're in at the moment in our particular solar system. We are not running into all the dangerous areas of our galaxy. But just as I'm about to go in, I'll briefly refer to the aspects from on guard, and that is the scale of our universe, just to put some measure of what is a reasonable scale to think about as we go and look at the various fine-tuning that I'm about to talk about. First of all, Big Bang. If we think of the Big Bang of being an apparent time of 13.5 years, certainly visible light that we see, then there have been 10 to the 17 seconds. So 10 to the 17 is a fact that scopes all of the appreciable apparent time that we see as we look out to the farthest reaches of our universe. Also, there are 10 to the 80th subatomic particles in the whole known universe. So there's a scale. 10 to the 17th seconds for time, 10 to the 80th subatomic particles in the whole known universe. Right, gravity. We'll talk about the fundamental forces and get into how finely tuned they are. Gravity operates over greater ranges but depends on mass and the inverse square of range. Electromagnetic force depends on a number of excess charges on the electrons or in our matter, and the inverse square of range. The strong nuclear force, not something we're actually able to touch or feel, but it binds the quarks to form protons and neutrons, then binds them together in the atomic nucleus. But it is effective only at extremely short distances. In other words, the distance of a nucleus, the radius of a nucleus. Weak nuclear force operates over the same range, and that binds neutrons' quark configuration, but is effective again only at that very short range. Now, this is why I particularly chose that particular book that I'm using, because it actually gives graphs. We can start to look at the graphical significance of the fine tuning. It's one thing to have lots of words, but it's better to be able to plot it on a graph, and we'll see the significance of it. This is the graph that shows that the stability of the stars, our sun for instance, depends on the magnitude of gravity versus electromagnetic forces. Those, of course, are the forces that operate at large distances. On the left, you have the vertical axis. We have the gravitational force constant. Of course, in the case of Earth, it's in our universe that we know, 9.8 meters per second, which represents unity there on the midpoint of the vertical scale. And then, using exponential scale, we go up to 10 to the 10th and 10 to the minus 10th. Similarly, and I'm afraid I don't know the actual constant, the electromagnetic constant, but that represents unity on the bottom, on the horizontal scale, represents what ours is in our universe. You will see that stable stars will only be available in this particular region here. Now, it looks a fairly big triangle, so you say, well, yeah, so what? There'll be lots of locations in here that we could have a universe that was different from ours and still get stable stars. I just want to point out something though. The vertical scale only goes up to 10 to the 10th. If you extend that up to the scale of the strong nuclear force, that goes all the way up to the 10 to the 50th. In which case, that particular triangle would comprise less than 1 part in 10 to the 35 of the whole plot. If we were to make this scale taking in all the fundamental forces, then this particular triangle is very, very small indeed. And we're in that small triangle. Just a reminder, well, you got the triangle, surely you could tune up and down a little bit and be able to still have viable universe. If G is greater than 9.8 meters per second, in other words, up above here, stars would need to be smaller to avoid gravitational collapse, because in fact it would compress and become neutron stars. Smaller, denser stars would be unsuitable for life because they would emit high energy photons, such as gamma rays, which would sterilize the Earth. And that's indeed what we see when we look at the neutron stars from a very safe distance. They do indeed put out very powerful rays, and they would sterilize us very, very quickly. If in fact, though, we were to come down on a lower aspect, even down to 10 to the minus 5 of the force of gravity, what would happen then? Stars would need to be larger in order for gravity to counteract the thermal expansion. They would produce low energy photons such as infrared, warming the Earth like an oven, but without the energy for photosynthesis to work. Photosynthesis is the key to why that particular dot in the bigger triangle is where it needs to be. If the strong nuclear force were just a little greater, now we're talking, so I'll just go back to the heading here, strong force versus the electromagnetic force to leave. So we're now talking not about gravity and electromagnetic force, but rather strong force and electromagnetic force. If the strong nuclear force were just a little greater, protons would bind each other and our sun would burn through its entire hydrogen fuel, that's single hydrogen proton fuel, to form unstable diproton in about 1 second. In just 1 second, the sun would use up all its hydrogen in its standard form and produce diproton, something that cannot combine with neutrons to form the first stage of the nuclear process, to form helium. If it was just a little weaker, deuterium would unbind, preventing the first nuclear action step on the sun, according to Professor Paul Davies. Without deuterium, it's doubtful, rather, if stable, long-lived stars could exist at all. Well, continuing on with the theme. The previous slide looked at the strong force, now we're looking at the electromagnetic force. Needs to be relatively weak so that electrons orbiting the atomic nucleus can be rearranged, facilitating chemical reactions and forming molecules. In other words, covalent bonds, and for all those that know chemistry, yes, water, among others, is a combination of hydrogen to oxygen atoms, and they combine because the electrons can indeed be able to shuffle between and come up with a molecule that is then used, then is water. If the electromagnetic force were just a little stronger, protons in all but the H1 nucleus would repel each other because two positive charges would repel, and leading to a universe full of hydrogen but no other elements. And what was now this is to summarise what I've just shown in words on the previous 2 slides. playing these forces, in other words, the previous two slides together, off against one another, has a drastic effect on the universe with an almost imperceptible region of region of stability. This is the graph again. I took it out of that reference book that I'm using. You'll see here that it's just a very, very slender grey area just up the vertical axis there, between when I plot the nuclear strong force on the vertical axis against the electromagnetic force constant. A very, very slim region. You get a diproton catastrophe above there. You get proton unstable if the constant is too high, and will cause the protons to repel each other. And then we have deuterium unstable down here. There really is only one slim region right there. Otherwise, our nuclear production of deuterium and would not be possible. We wouldn't have any of the other elements that I showed you back on the periodic table. We wouldn't have carbon, we wouldn't have oxygen, we wouldn't have calcium, we wouldn't have iron, all the things that we need for life as we know it. Just a quick aside here about the strong force. The strong force were increased by a little more than 0.4%. Stars produce lots of carbon, but no oxygen. Without oxygen, there can be no water and no life as we know it. If the strong force reduced by 0.4%, then stars would produce lots of oxygen, but no carbon. Without carbon, carbon-based life could not exist. Some would suggest, well, if not carbon, why not silicon? But whereas carbon can form 29,000 compounds with hydrogen, silicon can only form 55. Silicon's equivalent of carbon dioxide is a solid crystal. Therefore, we couldn't breathe in it. It wouldn't be useful for plants to absorb. Now let's go, having talked about at the upper level of the nuclear particles, now I'm going down one layer again. Now let's go down to quarks. The relative masses of the fundamental particles, very important. Fine tuning is required of the masses of fundamental particles, down quarks and electrons. I haven't mentioned it so far, but a proton, it consists of 2 up quarks and 1 down quark, whereas neutrons comprise 2 down quarks and 1 up quarks. And if we plot the difference in mass between the two, it comes out at this level at about the 0.5 million electron volts. Our universe is in this region here. If the mass or difference in mass between the up and the down quarks was anything over 1 unit, up or down, then we get into these regions where there was either a neutron world only or a proton world only. Or if not, we'd have no atoms, because the nuclei would swallow all electrons if it was over this stage. It's again a very limited region that our current fundamental particles, the quarks, have in terms of their mass difference. It would not work without that very limited range. Values above the line, as I've already said, will below the line with a positive gradient lead to a sterile universe where no chemistry can occur. And again, only the life-sustaining universe will exist if the difference in the quarks comes to that point there. Indeed, just you thought, well, even so, that triangle wasn't that small. Well, if we now start to use linear scales rather than exponential scales, we would need a block at least 10 light years high. In other words, all the way to, in fact, beyond the star Sirius. If we were, in fact, to plot that little triangle, it would be all the way to Sirius, and in fact, almost all the way to Sirius, and then some, before we could actually see that visibility of just that small difference between the up quarks and the down quarks to be able to get life-supporting universe. Okay, that goes as far as the nuclear fundamental particles. Now let's go and talk about quantum mechanics and Planck's constant. An electron is a wave which is constrained to fit within a given orbit. And we get down to microscopic details here. Its wave-like properties, however, are strange. The peaks and the troughs indicate where the electron probably is and probably where it is going. Quantum mechanics becomes significant as determined by Planck's constant, which in our universe is a very small value of 6.6 10 to the minus 34 joule seconds. If it were zero, quantum mechanics would not operate and atoms would become unstable. If it were much larger, quantum weirdness would start to affect our everyday lives, making the world in which live in unpredictable. And in particular, I guess, rather than going off to any science fiction thoughts about that, even the ability of DNA to store information would be compromised if Planck's constant was much larger than 6.6 by 10 to the minus 34 joule seconds. So life as we know it with DNA to store its information would be impossible because you'd never know where the genes would be. They could be in any part on the helix. They might flip around from one to the other because of the probability of where they might end up. And that's not how we need. I'm not a biologist by any means, but as I understand it, the helix of DNA is in fact very much based on where the different letters remain, stand fixed, and then are passed down from one generation to the next. Now we're getting on to one of the things that the Astronomer Royal mentioned. The density of parts of our early universe must have deviated from the average density by only about 1 part in 100,000. Decreasing Q to 1 part in 1 million will prevent gravity forming stars, planets, and thus life. Increasing Q to 1 part in 10,000 would result in stars, or nearby stars, disrupting planets in their orbits, again, making life impossible. So where does all that leave us? I'm now going back to conclusions that the authors of A Fortunate Universe, Life in a Finely Tuned Cosmos, state at the conclusion of their book. Firstly, Luke Barnes has a PhD in astronomy from Cambridge University in the UK. He leans towards the view that fine-tuning is not accidental but purposeful. To him, the universe contains good things like free moral agents and all that they can do and learn and appreciate. These, he feels, reflect the intent of a creator. Barnes is quite well read on theistic arguments from a largely Thomistic perspective as well as atheistic responses. Just a reminder, Thomistic refers to Thomas Aquinas, a very great philosopher in the Catholic Church back about 800 years ago. We have had his life. We did that a couple of years ago. But yes, certainly Thomas Aquinas, well-known apologetic and famous apologetic that has been accepted by many as one of the great philosophers. However, the other author of this book, Geraint Lewis, Professor of Astrophysics at the University Institute of Astronomy, is more sceptical. He argues that the presence of evil and suffering makes God's existence unlikely. I would expect a morally perfect being to create a morally perfect universe. He sees a multiverse as a more probable explanation for fine-tuning. Ours is but one of a vast sea of universes, and each with differing laws of physics and properties of matter set at their birth through some cosmic roll of the dice. We find ourselves in one of the extremely few universes that can support life, the anthropic principle in action. So, an interesting contrast from the two authors, and a good lead-in to the next, or the final part of this presentation, the multiverses. I looked and read a number of articles and came up with this reference, you'll see at the bottom there, where 5 types of multiverses are described, or 5 possibilities. The infinite universes. We don't know the shape of space-time. One theory is that it is flat and goes on forever. This would present the possibility of many universes being out there. It's possible the universes can start repeating themselves. For instance, as we know, I said earlier on, our current view on our universe is out to about an apparent 13.5 billion light years. We can't see beyond that, and for us, that's where it stops. But if space-time is indeed flat and goes on forever, or maybe there was another singularity out there, one that we don't even know about. Maybe there's half a dozen, maybe a dozen out there, each of which could have then exploded and gone on, maybe beyond 13.5 billion light years, maybe less. But there could be many other universes out there. Bubble universes, another theory. Bubble universes comes from eternal inflation, based on research by this cosmologist, Alexander Vilenkin. When looking at space-time as a whole, some areas of space stop inflating, just as the Big Bang did, apparently inflated out to 13.5 billion years and then stopped. Others, however, will keep getting larger. So if we picture our own universe as a bubble, it is sitting in a network of bubble universes on space. Other universes could have markedly different laws of physics than our own, since they are not linked. Then we might have daughter universes. Perhaps multiple universes can follow the theory of quantum mechanics as part of the daughter universe theory. If we follow the laws of probability, it suggests that for every outcome that could come from one decision, there could be a range of universes, each of which saw one outcome come to be. It's all about probability. Mathematical universes explain the structure of mathematics may change depending on which universe you reside. A mathematical structure is something that you can describe in a way that's completely independent of human baggage. For instance, we do in fact put constraints on a number of our mathematical expressions because they describe the way of life that we see it. For instance, when Einstein came up with E was mc squared, it was based on, I remember the analogy he gave was a train racing along at almost speed of light along a long straight track. And he then said there was a light shone, I think it was on the side of the railway track. And when he worked it out, he came up with the theory, a special theory of relativity. And of course, from that was deduced it was mc squared. But what happens if you didn't have a long straight track? Maybe there are other ways to express it. But if there had been an Einstein in another university, could have come up with a different form of the E was mc squared. And so this particular proposer, Max Tegmark, says, I really believe there is in this universe out there that there is, and I'll read this again, I really believe that there is this universe out there that can exist independently of me, who continue to exist even if there were no humans. And the final one, parallel universes. If space-time is flat, the number of possible particle configurations in multiple universes would be limited to that particular 10 to the power 10 to the power 122 distinct possibilities. With an infinite number of cosmic patches, the particle arrangements within them must repeat infinitely many times over. This means that infinitely many parallel universes, cosmic patches exactly the same as ours, containing someone exactly like you, as well as patches that differ by just one particle's position, patches that differ by two particles' positions, and so on, down to the patches that are totally different from ours. Right, now, the M theory. I'm not going to go into too much detail here because Kevin dealt with this on our first presentation this year. Multiverse theory, M theory, currently supported by string theory. There are approximately 10 to the power 500 different solutions to string equations. Claim that there could be infinite number of universes. We just happen to live the lucky one that enables life. Potentially explains fine tuning in this universe. Its achievements. String theory uses no experiments that would provide new insights, but it has revealed profound mathematical relationships within the equations. It predicts the existence of the graviton, in other words, how gravity exists. It matches Hawking's predictions on black holes. It unifies all four forces. It's the primary candidate for the theory of quantum gravity. And I highlighted this one, it's the most popular theory in town. It approximated the standard model. Remember, I had the standard model up there of the different subatomic particles. It leads to a better understanding of quantum theory. It's adaptable to new evidence, and most importantly, it hasn't been shown to be false. Criticisms. It's good at explaining, but bad at predicting. Existence of dark energy is not predicted. unable to be falsified or verified. Any idea can be incorporated. Achievements are overstated, but more funding than warranted. Contradicts known facts, calculates amount of data vastly larger than measured. Failed to explain scattering of particles and particle accelerators. Should have been made more progress by now. Requires many particles, 18 standard and 18 subparticles, S particles, and no S particles have yet to be observed. Absurdly large number of options, overly flexible, and it was overly flexible. Before I just finish then on multiverses, I'm going to bring up that Stephen Hawking, just before his death, told Cambridge University in an interview the following: "We are not down to a single universe, unique universe, but our findings imply a significant reduction of the multiverse to a smaller range of possible universes." I'm going to include on this talk about the multiverses to say that right now we can see that even Stephen Hawking doesn't agree with all the preceding suggestions that we might have 10 to the power 500. He said a much smaller range of possible universes. It's ongoing. We're not there yet. We just don't know if this is a viable theory. So, as we come towards our conclusion, let's revisit Richard Dawkins. One of the greatest challenges to human intellect has been to explain how complex, improbable appearance of design in the universe arises. The natural temptation is to attribute the appearance of a design to actual design itself. The temptation is a false one, because the designer hypothesis immediately raises a larger problem of who designed the designer. The most ingenious and powerful explanation is Darwinian evolution by natural selection. We don't have an equivalent explanation for physics. We should not give up hope of a better explanation arising in physics. Something as powerful as Darwinism is for biology. Therefore, God almost certainly does not exist. That's Richard Dawkins from his God delusion. However, there was a response from Professor John Lennox. Just a reminder, John Lennox is the Professor of Mathematics at Oxford University. Certainly no slouch in terms of his intelligence. He points out that in recent years, and I checked it up, 1971 through 1993, even natural science has shown itself to make design inferences, notably in the search for extraterrestrial intelligence. I think we've all heard of SETI. NASA spent millions of dollars setting up radio telescopes, hoping to detect a message from intelligent beings somewhere in the cosmos. Remember, this is the whole scientific community was out there. Well, a major part of the scientific community, certainly in astronomy, was out there trying to confirm there was intelligence out there. Why then the furor when some scientists claim evidence of intelligent causation in physics, small furor, or biology, large furor, is a scientific method not applicable everywhere? I'm so grateful for John Lennox pointing out this great contradiction in the scientific effort that's been put in and over the last few decades. Thank you.
Okay, I'm got
So 15 minutes.
Sorry. Right. Do you need to Are you going to leave your screen up there?
I'm happy to leave it up, and in fact, it might be important in case someone asks questions. I might need to go back.
Yeah. Okay. All right. That's a good idea. All right. We've got some comments come up on the chat line.
Yes.
And so we'll go through some of those. We won't break for supper for obvious reasons, but you can still put your money in the money jar. All right. This is a comment from me. You're saying how fortunate the sun is.
Yeah.
and it has all these fortunate properties. But since there are billions and billions of stars, is it all that surprising an occasional star is fortunate?
Well, no, and I would accept that, but it's just one of a number. We could go to each of those constants that we talked about and perhaps think, what about this or what about that? But it just happens that our star is a very stable star in a very quiet region of our galaxy that therefore does not experience what most other solar systems in our galaxy experienced. I mean, it's not a 100% conclusion by any means, but it's certainly very significant point to make that our star is very, very special.
But like other parameters, such as constants of physics, like they have new universal application over the whole universe.
Yes.
But just being a fortunate star doesn't.
No, it doesn't. It doesn't. But I just wanted to bring out, it was a point admittedly that doesn't go to the constants as such, but it is one of the aspects, at least on the astronomy scale, that does point that out. And it comes out of the Science Journal to make sure that, and I guess it goes back to that original statement by Stephen Hawking, we're just one of stars. There's millions of them out there. There's nothing special about us. We're just a small one. Well, I wanted to make the point that Stephen made before his death. And in fact, no, our star is quite special compared with most of the other stars that are out there.
All right, Tom Daly made a comment in response to me. He said, I guess it depends on how many other lucky stars we find. Tom, would you like to talk on that?
Oh, no, I was actually just looking up. There's a couple of efforts. Is it Kepler and then the Sloan Digital Sky Digital Survey or something, where they're actually looking for stars and for planets orbiting those stars in a lucky fashion, like Stephen's actually pointing out. So there's a lot of effort to actually try and identify just how lucky we are.
Yes, fully agree, Tom. Yes, I have read somewhere, and look, I've not researched it, but that all the stars they've found, planets rather, they've found around stars so far are around stars that are not, certainly not congenial to the form of stable solar radiation that we have.
All right, I'll skip Joshua's apology for being late. Don't want to embarrass him at all. But Thomas, you also mentioned something about supersymmetric particles. What are you getting at there? Tom?
I think he's got his mic off.
Yeah. Well, welcome to the digital world. I think you're on mute. The extra particles, the 8 extra particles, are the supersymmetric particles, which did not show up in the Large Hadron Collider. So that was one of the predictions of string theory that it was making, and in fact they've actually sent physicists back to their drawing boards because none of those particles actually showed up at the energies that they were actually predicted.
Okay, well, thanks for that, Tom. Thank you.
Rodney made a comment. I think that Dawkins' argument is weak. Would you like to talk on that?
Yeah, I've heard that argument used a few times, like who created God or whatever, and I think life must ultimately be eternal. Otherwise, you've got a situation where something starts out of nothing. And I think even in that sort of a context, even evolution isn't really possible in a state of total nothingness. So I don't think that Dawkins, while he may be a scientist, is not much of a philosopher. So that was just my comment about that.
Yeah. The comment, yes, and Kevin, I think you would agree. Back in the early days, when we went through On Guard, that was one of the philosophical topics we asked: is there a designer of the designer? And I think William Lane Craig certainly does address that in the book On Guard.
I think John Lennox says when he debated Dawkins way back when, and then he asked him, and I'll probably butcher this, but it was basically Dawkins was saying if there was a designer, that had to be a really complex answer. And he said, "Well, Richard, you wrote this book, The God Delusion. Isn't the designer of the God Delusion a simple answer, but perhaps a more complex being?" And in John Lennox' smiling, gentlemanly style, he really did take apart this argument of the design, who designed the designer, because you either stop at matter being eternal or mind being eternal, and John Lennox does a great job of that.
Yeah.
Can you actually bring up Dawkins' argument?
Okay, I can do that. I'm just trying to work out how far. Here we go. Let's go back to. Right.
That's a great photo, by the way. I don't think I've actually ever seen that. That's profound.
It really is, yes. It really is, yes.
You need to go back to slide 2.
Oh, that one? That was about physics.
Oh, sorry. Yeah, right. Yeah.
That's that the one?
Yeah, it's this one. Yeah. And to me, the arguments gets weaker around about 0.6 and then transitioning to 0.7.
Yes.
It says we should not give up the hope of a better explanation arising in physics, something as powerful as Darwinism is for biology. So, but you don't have it really. We don't have this argument, but he then concludes that therefore God almost certainly does not exist. So he's relying on something at that point for which he has no evidence.
Exactly.
But it's worse. The conclusion doesn't follow from the premises.
No.
The conclusion has got, he might as well have said, therefore cold beer is better than warm beer. Mm-hmm. I mean, it's just completely got nothing to do with what he's argued.
But it is true, though.
What's that?
Cold beer is better than warm beer.
Oh, yeah. Yeah.
I mean, there is a tenuous, to be fair to Richard here, there is a tenuous argument there. Look, we do have an explanation for the design by using evolution for Darwin's for biology. Surely there must be an equivalent one, and therefore we don't need a designer because we'll find out something that is a natural explanation.
We don't know now, but one day we'll find out.
Yeah.
That's a very generous reading of his premises.
Yeah. Okie doke. Any okay, I think we've dealt with all the chat comments so far. Would anybody like to raise any other points?
Yes, well, of course, where I'm coming from is that the Bible is the Word of God, and God was the only one who was there. So whatever the Bible says about it is all that really counts. And that it's pretty clear from Genesis chapter 1 that there was 6 literal days, and that God spoke the universe into existence in some form, and that it was in 6 literal days, which involved, according to other scriptures, he laid out the universe like a sheet, or like when you're putting a sheet on your bed or whatever, he just put it in place. And of course you can argue about, well, hang on, how long does it take for the light to get there to here and so on, but there are even explanations about that, about how light traveled in infinitesimal, almost infinitesimally fast in the very early days and weeks of the creation, and slowed down. It's even slowing down now, and there's good evidence of that. It's slowing down very, very slowly now, but there is evidence of that, which is another story. But when you combine all the improbabilities you just talked about, and they're pretty fantastic, most of them, aren't they? And you combine that with the biological things, where about, maybe 150 years ago, the theory of evolution wasn't a bad theory, but when you've got all the details of how the DNA strands work and how incredibly sophisticated every cell is, etc., etc., it's just impossible that these things would come by natural causes. And as Christians, of course, we know there is a God, and that we don't have too much trouble believing most of that, although probably some of you do. I don't know where you sit, most of you, but So I really think that it's just laughable in a way how these guys go to the nth degree to try and prove there isn't a God, which is really what they're doing, in my opinion. That why, and something interesting I read the other day, that there's a tribe discovered about 50 years ago in the Amazon or somewhere, where they didn't have any idea of their background. As far as they were concerned, life had always been the way it is. Every other civilization group on the planet up to that point had always believed in some sort of creator or divine being or whatever. And then it wasn't until 1850 or whatever, when Darwin came along, that the first time ever that anyone had tried to sort of present a theory, which is all it is, a theory that proved, as far as they were concerned, that that all this could happen without a divine being. My point is that it's all just a whole lot of theory if you take a logical view, in my opinion.
Yeah, but with your start, you're starting with the authority of the Bible as your starting point. But and you're saying that's a Christian position. But why should other people accept that as a starting point? Why should non-Christians take you, believe you?
Well, there's really only two possibilities, isn't there? One is that there's a God who's a creator who designed the whole universe to suit mankind, when the purpose, according to the Bible, is to have a whole lot of extra beings share the eternities with him as his sons and daughters, if they're prepared to be obedient, etc. The only other alternative is that you have all this incredibly ridiculous theory of everything forming itself, and you of course got to go back to the Big Bang. I mean, how can you have a Big Bang from nothing? It's just ridiculous.
What about other theisms that are not Christian? They still believe in God, but they wouldn't necessarily believe the Bible.
Well, that's true, but the fact is that, you know, there is lots of evidence of the Bible having lots of miracles throughout Old Testament times and even in New Testament times, and there's an experience you can have of receiving the Holy Spirit and all that, which gives people a whole lot of certainty about how the Bible is believable and so on. So yes, you can argue the Muslims have got a similar sort of theory really about Allah or whatever his name is, but it's nowhere near as convincing as Christianity or even Judaism.
You then bear so you have to take on the burden of proof of demonstrating that the Bible is authoritative, rather than just assuming that.
Yeah, well, there is lots and lots of evidence that the Bible is true, and that's another long story.
So you're supporting that statement. So you can't just say start and assume that the Bible's the authority and expect other people to believe it. You actually have to establish that case first.
Well, that's true, but I'm sort of hogging the thing a bit. But as far as I'm concerned, they'd be much better off putting the time and effort into studying all the reasons why the Bible is true or not true. And if they do that, they've discovered that there's overwhelming evidence that the Bible is true.
Okay. I'd like to go back to the opening slide, Steve.
Yep, going back.
Or the second one.
Yeah, this is Richard Dawkins again.
Yeah, the Richard Dawkins quote.
There we go.
Yeah. So this is I asked Steve to insert this, so this is due to my interference. So this is on page 1 of the Blind Watchmaker, which he wrote many years before he wrote the God Delusion. And on this, he is saying how biology encourages us to look for design, but then he compares that with physics. He says, physics is a study of simple things that do not tempt us to invoke design. And I think the kind of what comes through from what Steve has presented is that's rubbish. I think he would actually, in the God Delusion, he's basically dropped that approach. He's saying that, all right, physics does tempt us to invoke design, but he's still looking for a way out. So he's basically changed his tune since writing The Blind Watchmaker.
Yes, that was one of his earlier pieces, wasn't it?
Yeah, and if you read the book, it's easy to criticise and show that this statement here is rubbish.
Well, physics is the study of the fundamental things,
Yeah.
but that doesn't make them simple.
No. And from what we've seen, physics does tempt us to invoke design very strongly.
May I respond, please, to Dennis briefly? You'll note, Dennis, when I talked about the Big Bang and the 13.5 billion years, I did say apparent, because we actually had John Hartnett speak to us some time ago, and he did remind us that the basis of what we observe as 13.5 is based on the inference that the light shifts, the Doppler effect that we see at the redshifting of the universe, certainly does seem to be 13.5 billion years out there. That's straightforward. If you believe in it's only due to Doppler, yes, fine. But there are other physics. Einstein's theory of relativity, both special and general, speaks about time dilation. So you can be in one part of the universe operating on a time scale that is different from the time being observed in another part of the universe, either due to the speed that you're traveling at or indeed the gravitational effect that you're in. The space-time can be warped. So to say that our apparent time of our universe is 13.5 years is a true, 13.5 billion light years is true from this point of view. But nothing to say that time hasn't been dilated at some stage over the course of a young universe, say, to say that yes, apparently 13.5 billion years, but that may have to take into account time dilation, which is very much part of Einstein's theory of relativity.
Mm-hmm.
Yeah, end of my statement.
One thing that's a little bit interesting is there is another force, a fifth force, that's been called the subtle force, and there's a book written about it called I have it written down here. It's called The Heart Code, and it's written by doctors. I won't go into too much detail, but it's written by heart specialists, starting with Christian Bernard, who was the first heart surgeon, and 4 or 5 others who became consultants after quite a few years, followed up the fact that many people, like about 10% of people who receive new hearts, have some sort of memory of the person's life that they received the heart from, and it's you know, you can only find out by going through a lot of mechanisms to find out exactly, you know, who that other person was. And when they trace it, they find all sorts of evidence that that's exactly true, and that this evidence is somehow stored in the heart. And it goes on a great detail about all sorts of things. And these guys, scientists, you know, medical scientists is really what doctors are. And they went to, it's quite an academic book in some ways, but at the end of it all, they've got lots of other examples about, you know, how you can pray. They actually said this, and this is why I bought it in the first place, that, you know, that some things are instantaneous, and that they've traced that to this subtle force, and which is faster than the speed of light, sort of thing. And they said, actually, if somebody in Sydney and somebody in Brazil are praying for somebody in London, if there's going to be a healing result, it's going to be instantaneous. It's not going to be at the speed of light. And there's evidence why they said that. And there's all sorts of other properties which are quite remarkable of this subtle force. It can't be proved experimentally in any way at this stage, but there's so much circumstantial evidence that they've uncovered that even they are saying, look, we've only got 10% of it here. This is like an iceberg. We hope others will follow us and come up with more evidence, but it's a sort of a spiritual force which has got lots of circumstantial evidence, and implies that it can be instantaneous. You can, you know, affect something on the other side of the universe, and hopefully one day, when we get our new bodies and so on, the Bible implies that we'll be able to do things throughout the universe. So anyway, that's as far as I was convinced when reading that book, that there is another force called the subtle force.
All right, getting back onto multiverse. One thing you haven't mentioned, Steve, is some of William Lane Craig's critiques. Like the criticisms of the multiverse theory for explaining design is that one is that the multiverse generator would have to be finely tuned, so just pushing the problem back by one step.
Yeah.
and the other was the Boltzmann brain criticism.
Yeah.
You familiar with that?
No, I know you prompted me on looking at that. I guess I just wanted to keep it fairly simple. I didn't want to get into too much detail, so I was aware of those arguments, but having put some 50-odd slides together, I wasn't sure how long it was going to go and whether I would overdo it.
Right.
So
okay. Did you want to comment on those two factors anyway?
Look, I didn't look into them, I'll be honest. I did not look into them. I just wanted to point out the multiverses and then conclude with Stephen Hawking's final statement. Well, there probably aren't that many multi-universes out there after all.
Yeah, can we go back to that, please, for a sec? Because I think that plays into exactly, I think, Kevin, you and I are probably thinking the same way here, because if there's not an infinite amount of multiverses, then how do you get the string landscape generated so that there's enough universes that we actually pop out? So the need, if there's actually some physics here that actually limits the multiverse that's generating the universes, then it's very, very unlikely that we will produce enough. In fact, I've seen actually even a number of the particle physicists and the cosmologists talk about this, of how many universes you'd actually need to be able to generate to have some sort of reasonable chance of getting a life-permitting one.
Yeah, you think the 10 to the 500 is a jolly big number, but is it enough?
Yeah, but that's right. But if you start limiting it, as Stephen Hawking's here, so can you elaborate on this at all, Stephen?
Sorry. Well, you've got the website down there. Look, it was a quote from, it was something I found on the universespace.com by this author Elizabeth Howe back in May 2018. I'm afraid I didn't dig down deep into it. It was just the fact that I got this statement, and having introduced the other possibility of a number of different types of multiverses, that's why I just wanted to make that conclusion, but I didn't go into depth.
Yeah, and the Boltzmann brain objection is that basically a Boltzmann brain is like a brain in a vat, and so they're saying what people who put forward this argument say is far more likely that our experience of intelligence and life will be produced by a brain in the vat called a Boltzmann brain, rather than the universe in what that we observe.
Can I argue with that just a little bit? It's
sure.
That we'd have a quantum fluctuation that would bring about a small space of order and a Boltzmann brain that would then sort of pop into existence, see the universe around it, and it would be all illusory, and then pop out of existence. And that little patch of order is enormously much more likely on a multiverse theory than is our finely tuned cosmos that we actually observe.
Yeah. So you're supporting the counter argument?
Yeah, I'm supporting you. I think, isn't that independent of a brain in the vat, or am I misunderstanding?
I'm not strong on it. You could pull the wool over my eyes.
Yeah, I think it might be slightly different used, but it's the idea that if there was no if we were to be coming in to existence by chance, then we'd be much I don't want to say infinitely, but huge numbers of orders of magnitude more likely to have little patches of order, maybe as small as a brain, that could perceive what was around it, fluctuating into existence and then going out. Certainly not the glorious universe that perhaps God describes when he gives Job his marching orders.
I think the theory has to assume that there have been numerous failed universes in terms of being able to create life and intelligent life for the theory to have any chance of working.
just that. I mean, the human brain is supposed to be the most incredibly complex piece of matter in the universe, and when you think about it, if you know anything about it, it is absolutely fantastically complicated. And they've taken pictures of it forming in the womb and speeded it up, and it's like a welder working on two hemispheres at the same time, or different welders, and they're doing different things in each hemisphere. It's fantastically sophisticated as all the bits join together, and just while I've got it, that the one thing he said, one of the guys said, is that, look, there can't be a God, because if there was a God, he wouldn't allow all this evil and suffering and death and so on. But the fact is, the Bible answers that question in Genesis chapter 1 again, where it talks about until he made everything very good, or good, and then very good in the case of when he created human beings, which is like perfect. And so the word perfect was used by that guy. But what happened then with the fall of mankind through sinful, which was actually disobedience to God, rebellion, if you like, well then, according to Isaiah, we all became subject to time and chance from that point on, that the universe or this planet was handed over to the forces of evil, of satanic or opposition spiritual forces are actually dominating this planet at the moment until the Lord returns. So, that question was answered clearly, in my opinion, by the Bible.
I mean, I saw a debate once between William Lane Craig and an English professor whose name I can't remember. And the English professor basically argued that evil doesn't mean that God doesn't exist. It could be that just that God is evil. And I found that it's certainly logically possible, that the presence of evil doesn't mean to say that God doesn't exist, but it may raise questions about the goodness of this God.
Since the fall of mankind,
evil is probably one of the greatest obstacles, emotionally at least, why humans tend to reject God, because we see so much brutal suffering in our world that it is hard to, it is a tough issue, and there are many attempts, numerous books written on evil, the problem of evil. It's a tough topic.
Well, once again, the Bible talks about how we are given free will, and that the fact is, he does many, many miraculous things, in today's life as well as in ancient times. We're all subject to time and chance, and that if he were to interfere constantly, we would suddenly feel like that we didn't have free will, that God was interfering all the time. So, we just can't have it every way, can we?
But evil's not just about what we do, our evil acts to harm others. It's also about natural evil, which we can't control. So that's a tough issue as well.
Well, that's true. I mean, the Bible implies that that there is an opposition, spiritual forces out there, sort of led by Satan. There are principalities and powers and all sorts of opposition stuff out there which we don't know much about, and it encourages not to look into it too deeply. And it appears that part of the reason for that is because we need to suffer tribulation in this life if we want to expect to have a life with the Creator where we've sort of proved that we can overcome obstacles. It's overcomers to the end who get saved. So it's part of God's plan that we would be subject to forces, including opposition from the people of this world who despise Christians, most of them, opposition from our own internal flesh, that, the lust of the eyes, the lust of the flesh, the pride of life, it talks about in 1 John, are our natural sort of fleshly things that are against the spiritual things that God wants. So we've got to overcome all these things. And yes, it's a battle.
Is there such a thing as gratuitous evil? What I mean by gratuitous evil, is there evil that's so bad that it really can't have any justifiable cause or justification as to why it happens?
Well, according to the Bible, you know, Satan opposes us. He's still the prince of this world, and according to the Bible, he is about deceiving. He's a deceiver. He's a liar from the beginning. He's a murderer, and he is something else. I can't remember. One of you will probably remember, but he's out to deceive us and to kill us and to destroy us. You know.
What's God's responsibility in this?
Well, he has let these forces loose because man fell in the Garden of Eden, and that we chose basically to hand over the control of this world until the Redeemer came, and then later on until the Redeemer returned. And we are, if we allow ourselves to slip up, we're going to be subject to these forces.
It comes down basically to how you define evil. What does evil mean? What does good mean? If without a fundamental definition of evil, you get nowhere on that one.
Yeah.
Basically, what most people call evil is what I happen to dislike, which doesn't really work except on a personal, subjective level.
Mm.
If we take evil to mean anything that is contrary to God, so if God is defined as good, and I think if you define God as God, then good naturally follows from that, because it would by definition, so therefore anything contrary to that you would call evil.
Oh, well, I'm not sure
Or
that
not
I would
God.
necessarily agree with that, because some
Yeah,
people,
it requires a bit more explanation than what I just put in there, I'm afraid.
you might want to call it subjective, but people's experiences, they might have some sort of subjective interpretation of them, but nevertheless, they're very real and significant to them.
Yes.
Someone who's lost their loved one or lost a child through terrible circumstances, and the grieving that these people go through is absolutely horrific. They may not be very open to believe that there's a good God.
I think we might be drifting away from the topic.
Yes, we are.
Can I bring it back? Because if you're looking at the picture that Stephen's showing, you're just talking about grieving and evil and suffering and stuff. You know, from this perspective, if this all just happened from a universe, from a multiverse, it's actually just been infinite and just generated everything, then really, if that little blue dot is insignificant, then surely that suffering and that evil and stuff you're talking about is even less purposeless and even less significant. I reckon that's a great photo. I reckon I'm going to...
I would agree with that. Yeah. I would agree with you on that point.
Yeah. All right. I think we should attempt to wind it up. So, Steve, you've kind of left. You've been very good, actually. You kind of haven't been come down and dogmatically saying you have to believe what I do. And you kind of left it open and relaxed about it, which I think is good. But what's kind of your overall conclusion on the matter?
I guess I'll go back to the conclusion that the two authors made when they, right towards the end of, here we go, you have Luke Barnes.
Yeah.
Obviously, probably I infer with him, knows good things. However, and this is where the presence of evil, obviously Geraint Lewis says for him, the presence of evil was the one reason he could not accept that fine-tuning was an argument for a good maker.
Yeah.
I guess that is a stumbling block for many, but I do take the opinion of Luke Barnes there on slide number, whatever it is, 42.
Yeah. All right.
Can I just, can you hear me?
Yes, we can.
Can I just add a couple of things? The fine-tuning argument for me as a novice is pretty extraordinary. Listening to Stephen's presentation just affirms that we really are on a unique Earth, a unique planet in a unique solar system with a unique star. Our sun, if our sun was 2% bigger or smaller, we wouldn't be here. If our moon was 2% bigger or smaller, we wouldn't be here. If we didn't have planet like Saturn, we wouldn't be here. There are over 200 plus, probably 400 plus fine-tuning parts to our universe. And I think what you were saying, Stephen, at the beginning about the particles and the way that, you know, all the elements that we need. If our universe was any bigger, we wouldn't have them. If it was any smaller, we wouldn't have them. What I find pretty incredible is the fact that these scientists can look at this material and still be dogmatic in their stance to say that it just happened by amazing coincidence. And I think for a scientist, they might be able to have that argument. But if you actually share this with people, just your common person in layman's language, they actually respond. That's my point. They really do respond. Now, I just want to add one last thing about the evil argument. I know Tom did a brilliant job speaking about good and evil. Would have been a little while ago. And there's something that we can refer to. But here's Ravi Zacharias's little blurb. If evil is real and not a construct in our own mind and really something to be shunned and is morally deviant, there is no way to sustain that without a moral being who is a creator. You see, when someone says there's such a thing as evil, they are assuming there's such a thing as good. When they assume there is such a thing as good, then they're assuming a moral law for which to differentiate between good and evil. When we assume a moral law for which to differentiate between good and evil, they have to pause at a moral lawgiver, but this is whom they're trying to disprove and not prove. Now, why do I come down to a moral lawgiver? Well, when we talk about evil, it is in reference to a person or personhood, which places intrinsic worth on the human person. Intrinsic worth cannot be sustained ideationally in a naturalistic framework. How do you give essential worth to a product of time plus matter plus chance? Now, you can see that one on Ravi's Why I'm Not an Atheist when he presented to Princeton University. It's on YouTube. Now, if you summarise that and you look back at the fine-tuning, I just sort of think, you know, guys, I just find it amazing, you know. We live in such a great world and there's amazingly tricky things happening, even with what we're going through at the moment. But there's still arguments for why these things happen. Why do viruses happen? Because we actually need viruses to control bacteria, you know. And so if you listen to all those arguments, you think, you know, if man didn't get in the way and stuff it up somewhere along the line, we wouldn't be in this predicament. So, yeah, that's just my...
Yeah, so basically you're saying you can actually twist the problem of evil around the other way to actually use it to actually argue for the existence of a moral agent.
You can, because if we are just time plus chance plus matter, then who cares and why do you even bother? And how can you even have a moral position on anything? Because, you know, like, and one good, I think, analogy is like, is a lion evil when it kills something?
Yeah.
No, it's not. It's just getting food. Is a person evil when they kill something? Most people would say yes. All right. Why do you say yes?
Unless they've got mental issues.
Yeah, unless they've got mental issues. But, you know, we all have this deep inner, thing about good and evil. It's just there, you know. So, but the fine-tuning argument, I think, is brilliant, and that's the reason why I actually ended up coming to reasonable faith, because it's just the standout obvious. If you actually present it and show people that, you know, if our sun was just 2% bigger, we wouldn't be here. How does that happen? You know, and it's just a fortunate, you know, like, it's funny, you know, I actually follow Luke Barnes on Twitter, actually in Sydney, which I thought was great, and he's a Christian. He's not overtly, and he does run a little YouTube thing about talking about this type of stuff. It does do your head in. But I think you did a great job, Stephen, of trying to present it.
Thank you.
Yeah, so well done.
Yeah. That was a really good way, a very different way of looking at it and presenting it. There's stuff there that I hadn't come across before, Steve. So thank you.
That's great.
Yeah, actually spelled out what some of the fine-tuning things were, rather than just talking about engineering.
May I say, what I particularly chose that appealed to me was the graphs that I'll show, that they were two-dimensional. So one might say, oh yeah, well, I can fine-tune this, or you can vary that one a bit. But you needed the two-dimensional, like the one I've just got up now, to show no, you tune one and then you'll lose out somewhere else. You've actually got all those different dimensions are all interrelated. And you try tuning one, you'll ruin it on another constant. So it's very important that it's all one package.
All right then. Thank you very much for your presentation. That is greatly appreciated.